I am Dr. Sudherson, Associate Professor, Department of Mechanical Engineering, Rogini College of Engineering and Technology. Today, I am going to discuss about the flexible drives, which comes under the subject design of transmission system subject code ME 8651. Dear students, listen to this video. Before we deal inside the subject, we can see about the course outcome. After successful completion of the course, the student should be able to analyze the concept of design in the flexible drive elements like belt, chain, and rope drives. The student should be able to develop the method of various types of gears with parallel axis. The student should be able to develop a method for various types of gears with inclination with axis. The student should be able to explain the techniques used in industrial design, multi-speed gearbox application. The student should be able to categorize a suitable design for cam, clutches and brakes for automatic application. Introduction. To transmit power, flexible elements such as belt, chain, and ropes are frequently used. Pulleys are mounted on the shaft and a continuous belt or rope is passed over them. In belt and ropes, power is transmitted due to friction between them and pulleys. In case of chain drives, sprocket wheels are used. Classification of drives. Drives are classified into two types: flexible drives, direct drives. Flexible drive classified into three types: belt drive, chain drive, rope drive. Direct drives classified into two types: gear drive, cam drive. Types of belt: flat belt, V belt, ribbed belt, tooth or timing belt. Selection of flat belt drive. Selection of flat belt drive, it depends upon the power to be transmitted, speed of driver and driven shaft relationship, service condition, speed reduction ratio, sender distance, positive drive requirement, space available. The belt drives are of the following types: open belt drive, cross belt drive. Open belt drive. Open belt drive used when sense of rotation of both the pulley is same. It is desirable to keep the tight side of the belt on the lower side and slack side at the top to increase the angle of contact on the pulley. Cross belt drive. In case of cross belt drive, the pulleys rotate in the opposite direction. The angle of contact of belt on both the pulleys is equal, as shown in following figure. The belt has to bend in two different planes. As a result of this, belt wears very fast, and therefore this type of drive is not preferred for power transmission. This can be used for transmission of speed at lower power. Belt materials: leather, fabric and cotton, rubber, balata, nylon core, camel care. Velocity ratio of belt ratio. The ratio between the speeds of the driver and driven, respectively. Velocity ratio N2 by N1 equal to capital D by small d, where capital D by D and D, small d, diameter of driver and driven. N2 and N1, N2 driven, N1 driven. Omega 2 and omega 1, angular velocity of driven and driver. Effect of belt thickness on velocity ratio. Considering the thickness of the belt, N2 by N1 equal to capital D plus small t divided by small t d plus small t. Effect of slip on velocity ratio. Slip is defined as a relative motion between the belt and pulley. The difference between the linear speed of the pulley rim and belt is the measure of slip. The slip reduces the velocity ratio of the drive. Slip can be reduced by following two methods: roughing the belt by dressing, by crowning the pulley. Let S1 percentage of slip between the driver and the belt. S2 percentage of slip between the driven and the belt. S total percentage. S1 plus S2 velocity ratio N2 by N1 equal to capital D by small d, 1 minus S1 plus S2 divided by 100 equal to capital D by small d, 1 minus total slip divided by 100. If thickness of the belt T consider, then velocity ratio N2 by N1 equal to capital D plus small t divided by small t plus t into 1 minus S1 plus S2 divided by 100 equal to capital D plus t divided by small t plus t 1 minus S divided by 100. Effect of grip on the belt. Let sigma 1 stresses in the belt on the tight side, sigma 2 Stresses in the slack side, E Young's modulus. Now velocity ratio, N2 by N1 equal to capital D divided by small d divided by Young's modulus plus root of sigma 1 divided by Young's modulus plus root of sigma 2. Law of belting. Law of belting states that the center lines of the belt, as approach the pulley, must lie in the plane perpendicular to the axis of that pulley or must lie in the plane of the pulley. Otherwise, the belt will run off the pulley. Power transmitted by the pulley. Belt. P equal to T1 minus T2 into velocity, where T1 equal to tension in the tight side, T2 tension in the slack side, V linear velocity of the belt, centrifugal tension. As the belt moves round the pulley, it would experience a centrifugal force which has the tendency to separate the belt from the pulley surface. To maintain the contact between pulley and belt, the centrifugal force produces additional tension in the belt. This is known as a centrifugal tension. TC. Increase the tension without increasing power capacity. TC, mv square, m equal to mass per unit length, T naught, neglecting the centrifugal tension, T1 plus T2 divided by 2. If considering the centrifugal tension, T naught equal to T1 plus T2 divided by 2 TC divided by 2. Maximum tension when the belt is subject to the centrifugal tension. So T equal to T1 plus TC. T equal to maximum stress in the cross-sectional area of the belt, sigma BT, where sigma maximum stress, B width, T thickness. When centrifugal tension taken on the consideration tension in tight side, T1 equal to capital T1 plus centrifugal tension. Tension in tight side is T2 equal to T2 plus TC. Then power transmitted by the belt B equals to T1 minus T2 into V. After simplification, power equal to T1 minus T2 into V. It shows centrifugal tension does not have any effect on power transmission. Ratio of driving tension of flat belt drive. T1 by T2 equal to E power mu theta. Considering centrifugal tension, tension ratio T1 divided by T2 equal to T1 minus mv2 divided by T2 minus mv2 equal to E mu alpha. Mu, coefficient of friction between belt and pulleys. Alpha, angle of contact or angle of wrap. Condition for maximum power transmission. The power transmitted is maximum when the centrifugal tension T is the 1/3 of the maximum tension. IT equal to 3 TC. Maximum velocity V equal to root of T divided by 3m. Stresses in belt. Sigma T, tight side tension divided by cross-sectional area. Sigma B, E into T divided by diameter. Sigma C, TC divided by B into T equal to mv square divided by B into T equal to rho V square. Maximum stresses in the tight side of the smaller pulley, sigma max equal to sigma T plus sigma B plus sigma C. Design of flat belt drive. Step 1. Selection of the pulley diameter. Utilize the velocity ratio d by d rho n1 by n2 and the page number 7.52. Selection of pulley diameter may be done. Step 2. Calculation of design power. Design power in kilowatt rated power into load correction factor divided by arc of contact factor into small pulley factor. Ks, K alpha, Kd, these are the factors. We can able to obtain this value. Utilize the data book page number 7.53, 7.54, 7.62 of the PhD data book. Step 3. Selection of belting, page number 7.54. Step 4. Load correction, 7.54. V equal to pi d n1 divided by 60. Step 5. Finding the belt width. Belt width equal to design power divided by load rating into number of plies. Number of plies also can be select from the data book page number 7.52. Step 6. Finding the pulley width. Step 7. Calculation of belt length L. These are the systematic procedure of flat belt drive. Design of V belt drive. Step 1. Selection of belt selection. Page number 7.58. Step 2. Selection of pulley diameters D and D using the ratio speed ratio d by d. Step 3. Selection of center distance, page number 7.61. Step 4. Finding the normal pitch length, page number 7.61. Step 5. Length correction factor, page number 7.60. Step 6. Correction factor for arc of contact, page number 7.68. Step 7. Service factor, page number 7.69. Step 8. Calculation of power capacity, page number 7.62. Step 9. determines the number of belt, page number 7.70. Step 10, calculation of actual center distance, page number 7.61. Step 11, calculation of belt tension T1 and T2, power equal to T1 minus T2 into V, page number 7.58. Step 12, calculation of stress induced. Stress induced equal to maximum tension divided by cross-sectional area. This is a systematic procedure for V-belt design. Thank you.